This is our third lecture in number theory, and the topic today is beginning chapter 2, looking at divisibility of the integers. Now, I left you last time with, we had looked at induction on the integers, the principle of induction on the integers, which we said really is the essential property that characterizes the integers in comparison to things like the rationals and the real numbers, which share a lot of the same algebraic properties as the integers in terms of the operations of addition and multiplication. But the integers is the set that we can induct over the positive integers, so to speak. But we'll mainly meet it as a proof technique. It'll occur throughout the course, and we began our practice with it, our workout with it, so to speak, in looking at this set of problems. So some of these we looked at in the classes in the second lecture last week. But I want you to continue working on these to try and get good proofs of all of these out. And then in the tutorial this Friday, we're going to work through any remaining problems with those. And I may even bring along another couple of examples to look at and discuss in the tutorial class, maybe related to divisibility that we're going to look through today. There's a couple of little bits. Yeah, there's the strong induction principle, which we didn't really say much about, but that will occur. Strong induction is simply where when you're performing the induction step, it's not so easy as just proving that P of k minus 1 implies P of k. This is the situation where you may have to draw upon using not just the assumption P of k, or sorry, as it's quoted here, P of k minus 1 to prove P of k, but some or all of the previous ones. P of k minus 2, P of k minus 3, and so on. So strong induction is the principle that allows you to, in your induction step, is you can assume the truth of all previous cases of the statement when you're trying to derive or prove the following case. Okay? It's equivalent to the normal principle of induction that we've seen, and it's just a rephrasing of it, and in certain kinds of proofs it'll be a technique to use. Okay. So we'll try and bring some examples of that to the tutorial as well. Okay, but we'll keep a good pace and we'll move on into chapter 2. So chapter 2 begins with definition. This is the relation of divisibility on the integers. So number 30, where you already have the idea that it's to do with the study of the integers and the prime numbers. So that's to do with the operation of multiplication. So divisibility is really a technical way or a formal way of expressing when integers are related to other integers via the operation of multiplication. Okay, and it corresponds exactly to the very simple kind of primary school notion that you would have talked about in some kind of language in primary school, the notion of one number evenly dividing into another. Okay, so you're familiar with the idea that if you had 12 sweets, say, possible to evenly divide those 12 sweets among 3 people, because you can give them each 4 sweets. Okay, you're stuck and you've got a problem if you've got 10 sweets and 3 children in front of you, and you want to evenly divide the 10 sweets between the 3 children, because 3 does not divide 10 evenly. Give them 3 each, but then you're left with a remainder 1, and there's an argument over who gets. All right, technically, but then it's really just 9 sweets. Okay, so you're familiar with this idea. You would have either talked about the notion of one number evenly dividing another, or something, some kind of notion like that. And we're just going to do the same. We're going to talk about the same concept, but we're going to give it a very clean, formal, technical definition, and then we're immediately going to be concerned with proving a whole bunch of statements about it, and getting very firming up our ideas very carefully about what properties the relation has and what properties it doesn't. Okay. So the relation is divisibility, and it's defined here in 2.1. And we say, so we're talking about 2 integers a and b. We say that b divides a if we can express A as a product of integers, one of which is B. Okay? So B divides A, or B divides into A, if you like, if A can be written as a product of integers, a B times C, one of which is this integer B. Okay. Could be that the other integer C happens to be B also, in which case A would be equal to B squared. Okay, but if you can write A as a product, B times C. And similarly, of course, you would immediately also say that C divides A as well, when you see that there, okay? Because A is written as a product of integers, one of which is C. So you could say C divides A and B divides A. Okay. Now, okay, other language we can refer to B and C as factors or divisors of A, and A as a multiple of B and C. And the notation we use is B straight line A, okay? It's what's known in computer programming as the pipe symbol which on a standard UK keyboard is above the backward slash, right beside the Z. Or that's how you produce it, kind of. But it's just a straight line symbol. So if you're working in LaTeX, that's how you type it. And if we want to say that B does not divide A, we can put a line through it, just like you put a line through the equal sign when you say A is not equal to B. You can put a line through the divide sign to say B does not divide A. Now that's the notation. You read it in English as saying B divides A. The thing on the left divides the thing on the right. Now straight away, before we start getting into working with this, just a warning, you know, that there is a potential to get the order the wrong way around. So when you write A straight line B, you mean A divides B, but it's quite common for me to see students working where they get the order of the things mixed around, or they interpret the symbol wrongly. Okay. So just if you're prone to making those kind of errors, just be aware that this is a likely candidate that might cause you a bit of trouble. So just be very careful and try and come up with a good way of remembering that it's the thing on the left, your left, that divides the thing on your right. Yeah. Okay, so A divides B means we can write B as a multiple of A, an integer multiple of A. Okay, so like some examples. So 1, 3, and 5 and 15 all divide 15. Okay, so you can write 15 as a product of any of those integers, 1, 3, 5, and 15. Whereas, for instance, 10 is not divisible by 3. I want to divide 10 sweets between 3 children. There's a problem. Okay. Now, in formal logic terms, we call divisibility a relation. Okay. This device, B straight line A, it's a binary relation. It takes two things from a certain domain, namely 2 integers. It doesn't give you a numerical value. It's not an operation that gives you a numerical value. It's an operation that gives you a so-called logical value. It gives you something, the statement B divides A, which would be true or false depending on properties of B and A, what values they have or what we've assumed about them, and so on. Okay, so it's called a relation, a binary relation. So the binary refers to the fact it's got 2 inputs, and relation means that it's some kind of formula, if you like, that gives you a statement, something that is true or false. Okay, so straight away we're going to start proving something with these. The proof isn't in the book, so we're just going to work through it on paper and pen and talk about things carefully as we go. And all of these properties of divisibility in Theorem 2.1 have very short 1 or 2 line proofs, maybe 3 at the most. But they're all key, you know, very important properties, and things we'll be referring to again and again and again throughout the course. In particular, property 3 seems to rear its head on almost every page of the rest of the notes. So, you know, these are important kind of working properties that we'll want to be using all the time. Okay. So I'll just. Yeah, I meant. Oh, yeah. Okay, so the recording is just going to show my t-shirt talking about those. It was supposed to be following the screen, but anyhow, I'll get into the swing of things soon. Now, the recording setup in this room is a little bit awkward, but just because of the sneakers, I should maybe put the laptop up there. We'll see how this works. So theorem 2.1, we want to work our way through proofs of all of these. Document camera, on, lights, camera, action. Okay. So you can help me prove these, of course. As I say, they're all just kind of one or two liners. These are properties of divisibility. Some of them have kind of names attached to them. So this first one is reflexivity. So reflexivity is a property that a relation might have. Reflexivity is the property that a relation has if every element from the domain is related to itself. So the claim here is for every integer a in Z and the integers, A divides A. So why is that true? So we give ourselves an integer A. Now all of these have to be justified with reference to the definition. Okay? You've got a very clear definition over there in definition 2.1, the previous page. And it says, well, here we're trying to prove that A divides A. So A divides A, what that means is that we can write A as a product of two integers, one of which is A. If we can do that for every A, then we can say that A divides A. So can we do that for every A? What? How do you do it? 8 times 1, yeah. So the other factor has to be 1. In almost all cases. Okay. So A divides A. Simple. Yeah. It's short and immediate. Yeah. So every integer divides itself. Okay. Transitivity. Transitivity is a technical term we use about relations, about binary relations, when, a good way of remembering it is when the relation can travel through intermediates. So this means, you see the statement here, we've got 3 integers, so I'm not going to repeat the statement is in the notes there. We've got 3 integers, we assume A divides B, and B divides C. Yeah. And we want an argument that finishes with the conclusion that A divides C. Okay. So A divides B, B in turn divides C. So A is related to B is related to C. And transitivity says in all cases when you have those facts, the relation will travel through the intermediate B, so to speak. So A will divide C. Now this may seem nice and intuitive to you. You may understand what it's saying. You might agree with it. You might have no doubt at all that it is true. But for our proof of it, we want a clear argument that firmly proves this based on the definition. And maybe some earlier properties about divisibility that we might have accumulated so far, but we've only accumulated one, so probably not, okay? So we want to go back to the definition all the time. I've left a little gap here, hope that I can fit it in. So, like, what would be this, in terms of the definition, how can we say that A divides C? We can only say that if we know that C can be written as a product of two things, one of which is A. Yeah, that's the definition. A divides C, if C can be written as a product of two integers, one of which is A. Now, starting at the end and working back a step helps you to kind of structure your proof, because you can see now that what your task is. Our task is to determine or show the integer that goes in that gap. Now, which integer goes in that gap? Well, it's going to be made up of the complementary factors from these two divisibility statements. Okay? But they aren't in the scene yet. They don't have names, so we should introduce names for those. So if we know that A divides B, we can say that B is equal to something times A. May as well call it a alpha, say. B is equal to alpha times C. Sorry, alpha times A. And C is equal to beta times B. And this is for some alpha, for some integers alpha and beta. Of course, alpha is the integer given by the ratio B divided by A. Beta is the integer given by the ratio B divided C, of course. We tend to, I don't know, we tend to maybe avoid working too much with fractional quantities. We tend to introduce other names for them because everything has to be done in the integers here. We don't ever want to start claiming that something, one integer divides another when it doesn't. Okay, so I don't know. We tend not to use fractional quantities in our arguments. Not all the time, but it's perhaps cleaner when we don't. So C is equal to beta times B. So what goes in the gap here?
Alpha beta.
Alpha beta, yeah, because just substitute what? We're going for C on the left. So we substitute this B with alpha times A. So you've got beta alpha, alpha beta, whatever. This integer times A. So, oh my God, why didn't anybody pick me up on that? That shouldn't be the divide sign there. That should be the equal sign. Equals. Excuse me. That's C equals beta alpha times A. You spot me making slips like that? Correct me immediately. Okay, so that's a proof of transitivity. We started off with two divisibility statements, A divides B and B divides C. We reached a conclusion that A divides C. Okay. Property 3. Now this seems to be a crucial one. Divisibility of linear combinations. And you can kind of get a clue. For this one, I'm going to write out the actual result. So if A divides B and A divides C, then for all n and m, A divides the same way, nb plus mc. You can maybe get a clue about why it might be so crucial, because it's linking together divisibility with the operation of addition. It's linking together those two. And that's maybe a clue as to why it seems to be invoked a lot of the time. So this thing, NB plus MC, we can call that a linear combination of A and B. Okay, that's why we have the title. NB plus MC is a linear combination of B and C with coefficients n and m. And the coefficients have to be integers. Okay, so everything we're doing here is about the system of the integers. Okay, well, this is an if-then statement. So the first thing to try is just to try and prove it directly. So you assume all of this stuff here, assume the conditions, and you try and argue for the conclusion. Okay. Noting that your argument for the conclusion has to work for every single pair of integers n and m. So you can't assume any special properties. N and m can be any old pair of integers at all. So we assume A divides B and A divides C. The conclusion we're going for is that A divides NB plus MC. Okay. It's good here to start from the end as well. You know, how can you make a conclusion about divisibility only if just before that you'd satisfied the definition of divisibility in this case? Okay? And that definition here will be if we can show that this integer, nb plus mc, happens to be a product of two integers, one of which is a. Okay? That's what the definition says. B divides A, this divides that, if and only if we can write that as a product of this with something else. Okay? So in order to make the claim that B divides A or whatever, you have to establish an equation of this kind. Okay? If you're proving things directly just from the definition. Okay? So this is our task. This helps you structure your argument. It shows you what you have to do. You have to find the correct integer that goes in there. Yeah? It's not going to be a particular integer because we're not dealing with, you know, everything is just variables. So that it's clear that the thing that goes in here must be made up out of the B, the C, the N, and the M. It must be something to do with all of those, and A. So those are all the ingredients, and this is going to be some kind of expression involving all of those. So you just patiently work your way towards it. Go back to your assumptions, roll your assumptions forward a little bit. By that I mean, you know, interpret the definition. So A divides B, what does that mean? It means B is equal to something times A, say beta times A, and C is equal to something times A. Also, let's say C is gamma times A. Beta and gamma are the, no, so for some beta and gamma, some integers, beta and gamma. Okay, so we've introduced the complementary divisors. Everything's in the picture here. We want to start, we want to prove something about this, NB plus MC. What do we want? We want some kind of an expression for it involving A. Here are two expressions for B and C, both of which involve A. So we could just go for direct substitution into here. That will bring in the A. So this is going to be N times beta A plus M times gamma A. Okay, we won't waste time separately. Remember those axioms for the integers, distributivity, associativity. Okay, we're not going to separately justify each and every one of these steps. We'll just assume that as working algebraic knowledge of the integers. Now, technically, there's associativity and stuff going on here. So what's going on here? Well, you see, you want the A to be factored out, so you just do it. So this is N beta plus M gamma times A. Is this thing an integer? N times beta plus M times gamma? Is that an integer? Yeah. It's the four parts of it that are multiplied and added together. They're all integers. So you just get another integer. Okay. So we've fulfilled the definition. We've been able to write this linear combination, NB plus MC, something times A. Therefore, we can conclude that A divides that linear combination. Did we at any point make any special assumptions about N and M? Did I assume anything in particular about them other than that they were just integers? No, I don't think so. Okay. All we used is just their properties in terms of manipulating sums and products. Okay. So certainly there's we proved it for all pairs of integers N and M, not for any of it, okay? So that's a direct proof of that implication, that if-then statement. Okay. Any questions about those first three? Reflexivity, transitivity, and divisibility of linear combinations. Before we continue with the other ones, I'll insert here So reflexivity and transitivity are two nice properties that a relation might have. You often see them in the company of this relation, symmetry. And when a relation has those three properties, reflexivity, transitivity, and symmetry, it's referred to as an equivalence relation. But divisibility is not an equivalence relation. So symmetric is the property that says that if A divides B, then B divides A. Symmetry, if the relationship goes one way between a pair, it goes the other way as well. A symmetric relation. So how can you prove that divisibility is not symmetric? Well, this would be for all A and B, for all integers A and B. That's what symmetric means. So how would you prove that divisibility is not symmetric? Well, you don't need a general argument for it, because if you want to prove that this kind of thing is not true, this statement says for every pair A and B, something is true. Well, to prove that's not true, you just need one counterexample. One particular pair of integers A and B, such that that implication fails. So who's got a counterexample for that divisibility is not symmetric? So you want an A that divides a B, but you want the B to not divide the A. And more or less any divisibility, any example would work. 4 and 2, good. So 2 certainly does divide 4, fine. But 4 does not divide 2. You can't write 2 as a multiple of 4, where both factors are integers. If you allow yourself to be in the domain of the rational numbers or the real numbers, of course, then you would say that 4 does divide 2, because 4 is a half, or 2 is a half times 4. So, but we're just in the domain of the integers, of course, 4 does not divide 2. So it's not at all symmetric. So that's just a quick interlude. So on with these properties, properties 4, 5, 6, and 7. 4, 5, 6 are particular kind of things. 1 divides everything. So let A be an integer. So 1 divides everything. So that means, can we write A as something times 1? Yes. No, you've fallen victim to that warning gate. So when we read this, we read it as 2 divides 4, meaning that we can write the thing on the right, we can write the 4 as a product of integers where one of them is 2. So 4 is 2 by 2. Yeah. This is saying 4 does not divide 2. So this is saying you cannot write 2 as an integer times 4. Indeed you can. Yeah. Do you know where it's confusing? The reason it's so confusing is because, so you know, sometimes you might write fractions like that. Yeah. And there you're right. There it is the 4 that's doing the dividing. There, when you write a fraction like that, 2 over 4. 4 is dividing into 2, so to speak. But when we use the straight line vertical symbol like this, 2 divides 4, that's referring to, the thing that's referring to is the fact that you can write 4 as something times 2. So it's the 2 that's doing the dividing into 4. And this isn't my horrible invention, the fact that these two conflict, kind of, it's just the way it is. Yeah, it's how this notation has arisen. Okay, so this is where the contradiction happens. So just be aware of that and don't get trapped by it. So why does 1 divide everything? 1 times anything is itself. So in particular, 1 times A is A. Yeah. So short and sweet. 1 divides everything. 0 divides only itself. 0 divides only. So 0 divides hardly anything. Nothing, in fact, except for itself. That's what that's saying. So if you ever encounter a divisibility statement that 0 is dividing A, that means A has to be 0. That's what we're proving here. Well, according to the definition, this means A is written as something times 0, B times 0 for some B, some integer B, but whatever integer that is, when you multiply it by 0, of course, you get 0. So 0 divides nothing except for itself. But on the other side, going the other direction, everything... I'll mix them up. So that's property 6. This is property 5. Sorry, excuse me.
In ours, 5 is everything divides 0. So what you wrote was right, but what you said was
No. No.
Is that not everything?
No, that is saying if
I'm doing it now.
you're mixing up the direction. If 0 divides something, something being A, that something has to be 0. So 0 only divides itself. You can never find anything apart from 0 in this position here, paired with the 0 on the left-hand side. That's property 6. Let's skip it. Property 5 is everything divides 0. So if you let A be an integer, can we write 0 as something times A? Can we? Can you write 0 as something times A? Something being an integer. 0, yeah? That's okay. 0 is a perfectly good integer. So if 0 is equal to a product of 2 integers, one of which is A, this means A divides 0. And A was any old integer. We didn't use any special properties of that. Okay, so those are things that sometimes people flip in their minds as well. Everything divides 0. 0 divides nothing except for itself. Okay, then the last of these properties is kind of a cancelling property or a simplification property. So if we let A, B, C be integers, and this is an equivalence, if A divides B, if and only if A times C divides B times C. Well, A divides B, I mean, that's equivalent to, under the definition, that B is equal to something times A. This is equal to an alpha times A, or some integer alpha. But that is certainly equivalent to multiplying both sides by C, which would be equivalent to CA dividing BC. AC dividing BC. So we can go back and forth with introducing or cancelling factors from either side of the divisibility statement or relation, with the one proviso that, of course, the C must be non-zero, because for the equivalence to work backwards, for the middle line to imply the one above it, it must be that C is non-zero. Because if C was 0, you couldn't cancel it from both sides, because you can't divide by 0. Okay. So any questions about any of those properties that you'd like to ask? And they're all fairly reasonable properties. Probably all of them, like, it's not a surprise to you or anything, those properties. They're all things you're familiar with, I'm sure. But what you do notice is we've given a very clean formal definition to divisibility, and that allows us to construct rigorous proofs, just simple 1 or 2 line arguments working with the definition that prove these properties. Okay, so once we've got the notion of divisibility, of course, we can immediately define, one of the central objects of interest here, which is what a prime number is. And again, I'm more or less assuming everybody knows where at this definition, but of course, so an integer is prime if it's strictly bigger than 1, and it has no positive divisors apart from itself and 1. Invariably, we use p to denote primes. So if you're in a number theory course, whenever you see p, probably, unless the author's being particularly cruel, that p will be representing a prime number. And when you want another variable name to talk about prime numbers, we tend to use q. And maybe try and do everything with p's and q's. Okay. And here's the list of prime numbers. So 2 satisfies that definition. 3, 5, 7, 11, 13, 17, 19, 23, etc., etc. Okay. So these are all numbers which which have no positive integer factors apart from themselves and 1. Okay. So 2 is a prime number. It's the only even prime number. So often when you'll see in books and when people are talking, they refer to odd prime numbers. So the odd prime numbers are all the prime numbers except the first one, 2. 2 has some special properties, and it often has to be left out of statements concerning primes. So a lot of the times, statements about primes might refer to odd primes or large primes. So large primes, something bigger than 2 in some ways. Okay, now, this is an interesting definition, and one of the reasons why we care about that, or might make that definition, is something that's coming up in the next chapter, which we're working towards, and this is called the fundamental theorem of arithmetic. The fundamental theorem of arithmetic says that every positive integer n factors into a product of primes. That's one part of what it says. Then the crucial part, number theory in the integers anyway, the crucial part is this, well, just as crucial as this second part. This factorization is unique to that integer n. And by that I mean that if you factorize n into a product of prime numbers, there's only one way to do it, essentially. Trivially, you might reorder the primes in the product. So you can write 15 as 3 times 5. You can also write it as 5 times 3, but we don't regard 3 times 5 and 5 times 3 as being different factorizations. It's the same 2 prime numbers, just flipped around. And multiplication, we know, is commutative, associative. So you've got a big long product of prime numbers. Yeah, you can mix up the order in which they occur in the product, but that's not really a different prime factorization. So the fundamental theorem of arithmetic says everything can be factored into primes, and that factorization is unique. Now, most people's, as it says here, of course, most people's intuition agrees with this. It's a familiar fact that nothing surprising about it. But the uniqueness part, it's not like, okay, 15, okay, you can't write that as any other way. It's product of prime numbers apart from 3 times 5, and you can pretty easily satisfy yourself to that fact because there's only a small number of prime numbers less than 15. You try all possible products, the only one that works is 3 times 5. So you've no trouble believing that 3 times 5 is the only way to write 15. But if I present you with a integer which is a representation in the billions of digits, I mean, how can you be sure that there's one and only one way to express that large integer as a product of prime numbers? It's something completely outside our intuition. We've no way of, at all tasting or appreciating that, what's going on with the numbers in our minds. So we need a rigorous theory to establish that. Okay, and it does take a surprising amount of, it's not immediate that you can prove the uniqueness part. Okay, so that's the proof of that is coming in chapter 3. What we could probably describe is a proof of the first part of it. Okay, so the FTA is our acronym, our abbreviation of the fundamental theorem of arithmetic. And we could say here we can prove the existence of prime factorizations immediately. But not uniqueness. Uniqueness requires a little bit more knowledge about properties of divisibility and so on. Okay, so for example, so we'll just illustrate the idea here. I mean, it's something you are entirely familiar with. Trying to think of a good example, particularly good example. Yeah, 68. Okay, you take some integer. Either it's prime or it's not. So is it prime? Okay, this is not prime. So we then write down some kind of factorization of it, any old factorization. So 68, is it prime? No. So 2 by 34, and then you ask the question, are they all prime? All the factors you're looking at? Okay, 2 is prime, but of course 34 is not prime. 34 we can write as what? 17 times 2. Are they all prime? So basically you keep on factorizing all the leaves in the tree. So this is an upside down tree. Trees look like that, the base and the branches. Leaves are the things at the end of branches. Mostly in computer science and maths, trees go down, seem to. These are branches of the tree. So all the time we're asking, are the branches prime? Sorry, these are the leaves of the tree, the things at the end of the branches. Are the leaves prime? When you answer yes to that question, you're finished. You've got your prime factorization. Okay, 68. Is 2 times 17 times 2, or more compactly, 2 squared times 17. Okay, well, that's not a proof because it's only one particular example, but what it does describe or illustrate is an algorithm. So we could say the algorithm shown here, which says keep factorizing leaves of this tree until all are prime. Will produce a prime factorization of any integer. But the one thing you have to be careful with about algorithms is you have to know that they'll stop. But it's quite easy to see that this algorithm will always stop, because when you start with an integer up here, the leaves that are produced, if you look down any branch or any sequence of branches, the leaves are always, the nodes are always getting smaller. Okay. Since along each branch along each path of branches, the integers are strictly decreasing. Okay, because you're factorizing something to show this in prime, so that the integers are strictly decreasing. And so by the well-orderedness property, remember the well-orderedness property said that every non-empty set of positive integers has a least element. So that tells you basically that this process will stop eventually. No matter how large the integer is that you start off with, you keep factorizing the leaves. All the time the leaves, although they're multiplying, the number is rich in factors, the leaves will multiply, because each time you get, each leaf branches into 2 branches. So the leaves are getting larger and larger, but the numbers appearing at the leaves are getting smaller and smaller. So down any path, there will be a least element. So every path of branches is finite, so therefore the whole binary tree is finite. So sorry, I'm writing that quickly. So this will produce a prime factorization of any integer, since along each path of branches, the integers are strictly decreasing. And so by the well-orderedness of the integers, each path of branches or in this binary tree each path of branches in this binary tree is finite. So the algorithm will end. It's not the case that sometimes you get stuck in a loop where one of these branches will go on forever and you'll never get the prime. You'll never get a prime factorization. So what we're left here is this question, and this we'll be working towards settling this question in the next chapter. How do we know it's unique? The prime factorization. Okay, again, 68, this is that doubling. You can hold in your hand all the prime numbers less than 68. You can test all possible products, test all the ones that give products less than 68. You'll see that 2 2s and 117 is the only one that does it. But the question is, for a ginormous integer, there's like to be millions and millions of different possible factorization trees you can produce. The question is, how do we know we're always going to get essentially the same set of leaves at the bottom?